Okay, great. So yeah, so let's start. So we're very happy to have Professor Jennifer Cano from Stony Brook to join us and share with us some of her recent research. And Jennifer obtained her PhD from University of California at Santa Barbara. After that, she joined a Princeton Center for Theoretical Science as a postdoc. And it was at Princeton she developed the theory of topological band structures with crystal symmetry in a series of very interesting papers on topological quantum chemistry and elementary band representations. She joined Stony Brook as a faculty in 2018 and is also an affiliated associate research fellow at the Flatiron Institute. She's an expert on the classification, realization, and measurement of topological insulators and semimetals. So today, I think she's going to talk about a Moire lattice, Moire superlattice on the surface of a topological insulator. So without further ado, let's welcome Jennifer. And Jennifer, the floor is yours.
Great, thank you. Thanks for having me and giving me the chance to present some of the stuff that we've been working on. So I'm going to talk about two different things. In the first part of the talk, I'll talk about our work on going beyond the first magic angle. So probably I'll introduce this, but probably a lot of people are already familiar with twisted bilayer graphene, and all the experiments that are being done are at the first magic angle. And what we have found is that if you look at, there's other magic angles which are smaller and also have flat bands. And so if you look at these second or third smaller magic angles, you see different phenomenology, which we think could lead to exciting interacting physics. So that's the first part of the talk, and then I'll move to the main part, which is given by the title here, where we're trying to transfer the Moiré physics and graphene to the Dirac cone on the surface of a topological insulator. And what we show is that you can significantly renormalize the velocity of the surface Dirac cone on the surface of a TI, and this will enhance the density of states and enhance the instability towards interacting topological phases. So that's what we're going to talk about today. And our work is motivated by twisted bilayer graphene. So twisted bilayer graphene provides a tunable platform to realize strongly correlated phases. Its tunability is what makes it so exciting, as well as the variety of different types of correlated phases that have been realized. And so I've shown some of these examples here. On the left-hand side is the original data showing superconductivity and other insulating phases in twisted bilayer graphene. And on the right-hand side is the data showing quantum anomalous Hall effect. So not all of these correlated phases are completely understood, and that's not understanding those phases is a huge area of research right now, which is not the topic of this talk. But I do want to give some basic background on why it's possible to realize correlated phases in twisted bilayer graphene when we know that monolayer graphene is a very well described by a tight binding model and doesn't really display any correlated physics. And I think that this Bistritzer-McDonald model gives us a pretty straightforward explanation, which is that we can, in order to understand twisted bilayer graphene, we only need to look at the low energy physics. And the low energy physics is the Dirac cones in each layer. And so if we look at just one valley, then we get two Dirac cones from layer 1 and layer 2. And so they can be pictured like this. And the two Dirac cones are separated by some momentum, which is determined by the twist angle. And then they cross somewhere. And because there's interlayer tunneling, this crossing can gap, which is shown in this second picture. And so now if there's some kind of fine-tuned point when the strength of this interlayer coupling matches the distance between these Dirac cones, then this band will become extremely flat. And it's these extremely flat bands that enable the correlated physics to appear. So these are some band structures showing these flat bands. So on the left-hand side is the band structure for the model that I just described, this Bistritzer-McDonald model, which is a low energy model, just looking at the Dirac cones in each layer. And you can compare the density of states in freestanding graphene to the density of states in twisted bilayer graphene and see that there's a huge renormalization, the velocity. So you get this very flattish band appearing with a very large density of states compared to monolayer graphene. And the right-hand side is an initio calculation where the black bands are allowing the atoms to relax. And here you can see that you get a pretty flat band with a narrow bandwidth, less than 10 MeV, which is gapped to the conduction and valence band. So we'll call this the mini band. And because of how flat it is what gives rise to these correlated phases. So in our work, we don't actually study this full model. What we study is what's called the chiral model. It has an extra particle hole symmetry, and then these flat, nearly flat bands become exactly flat. So this is a really neat model, which was introduced in these two papers that I've cited here. And it has some cool properties that I'll discuss. One property is this, that the flat bands are exactly flat. And the other important property is that the wave functions are exactly solvable, and they bear some resemblance to quantum Hall wave functions. So, from that model, what you get is that there's 4 exactly flat bands, 2 in each valley. And those 2 flat bands each have sublattice as a good quantum number. That's what you get from this extra chiral symmetry. And so in each valley, you have 2 flat bands, and you can identify them as being on the A sublattice or on the B sublattice. And they're related to each other by symmetry. And that symmetry, since it involves time reversal, flips the Chern number. And so this is another attribute of this chiral model that makes it so useful, which is that now in each valley, we can say that we have 2 flat bands, and those 2 flat bands have a Chern number. And so that gives us some insight into where the topology is hidden in these flat bands. If you look at them together, they have net Chern number of 0. But if we have this extra symmetry, we can resolve the flat bands into one of plus Chern number and one of minus Chern number. And this also gives some kind of intuition as to why the quantum anomalous Hall effect can appear. If you take this twisted bilayer graphene and put it on top of hexagonal boron nitride breaks the sublattice symmetry. So it will pick out, say, 2 of the bands which are just in the A sublattice or just in the B sublattice. And so now in each valley, there's just 1 flat band, and that 1 flat band has a Chern number. So if there's any spontaneous symmetry breaking that will split the valleys, it needs to be a time reversal, spontaneous time reversal breaking. Then you'll be left with quantum anomalous Hall effect. So what we've done with this model is we've looked at analytical properties of these of the wave functions for this chiral twisted bilayer graphene model. And this work was led by Ji Wang, who's a postdoc at the Flatiron Institute. And so the first thing that we did is derive this extra inversion symmetry of the model. And using this symmetry, we can factorize the flat band wave functions. And so this flat band wave function looks intimidating, but we can see actually that it breaks up into simple parts. So I'm showing some spinor here. What is this spinor? It's the wave function in the A sublattice of a flat band, and it has 2 components, which are its weight on the bottom layer and its weight on the top layer. So that's what we call phi B and phi T. And then we can look at these components on the right-hand side, and we see that there's 3 parts. So the last part is a quantum Hall wave function. This is the wave function of the lowest Landau level. And this is what gives this flat band the topological properties like the Chern number that I just mentioned. The next term is an anti-quantum Hall wave function. It's a Landau level lowest Landau level wave function, but looks like it's in a reverse magnetic field, and it's at a fixed K point. And so this doesn't change the topological properties of the flat band because it doesn't have any dependence on the wave vector K. But what it does is ensure that the product of these 2 things has the block periodicity. And then finally, there's this third term. And so the interesting takeaway from this is that, as I said before, there's a series of magic angles, and I actually plotted them down here. So this is the first magic angle. It's around 1.1 degrees. And then there's a second magic angle, say around ½ a degree, a third magic angle around 0.3 degrees. So there's a series of magic angles where you get flat bands in twisted bilayer graphene. And at all those magic angles, this function rho is different, but these other parts of the flat band wave function are the same. And so this is the difference. This is the thing that makes the wave functions at the first, second, third magic angle be different from each other. And right, and so because it's different, as I'll show, then this leads us to believe that there can be different physics at these other magic angles relative to the first magic angle. And so how do we get a handle on this physics? What we first plot is the density of states in real space for one of these flat band wave functions. So the flat band, it spans all of the Brillouin zone. So we can pick out different flat band wave functions at different K points. And for each one of those wave functions, we can plot it as a function of real space. And so what we're looking at here is a plot of the wave function at the K point plotted in real space. And so we see, and then it has a weight on the bottom component, bottom layer, and weight on the top layer. And we see that for both of these, there's a peak at the center of the unit cell. The center of the unit cell corresponds to AA stacking between the two graphene layers. And then there's these vanishing points at the corners where the density of states vanishes. And actually, we can show analytically that these are exact zeros where the density of states, it's a node in the wave function. It literally vanishes. And so the first check here is that we can compare this to experimental data and see that it agrees with what's seen in the experiment. So this is kind of a reality check because we've been looking at this simplified model of twisted bilayer graphene, but the density of states agrees. And so what I mean by agrees is that if you look at the density of states for twisted bilayer graphene, you get this series of peaks. There's one peak per unit cell, so they form a triangular lattice. And that's exactly what we would see here if we took this wave function and repeated it translating it by the lattice vectors. So that's our reality check. This agrees with the experiment. And so then what we can do is compare. This is the plot that I just showed at first magic angle, but we can then compare this charge density and plot at the second magic angle and at the third magic angle. And what we see is that there's a different pattern in the density of states. At the first magic angle, you see this peak at the AA positions. And then at the second magic angle, what happens is that you get an increasing number of nodes at the center of the unit cell. And this pushes that peak out. So instead of being a peak at the AA site, it's vanishing in the center, but then you get a peak in the density of states around the AA site, this kind of ring of peaks here. And as we go to the third magic angle, this effect becomes even stronger. You get 6 nodes in the wave function, and then like kind of a ring structure of peaks around. And so this is our first prediction, which is that if you looked at the smaller magic angles, that you would see a different pattern in the charge density. And these types of patterns are different than have been observed before. There's an important consequence of this, which is that the interacting physics is determined by projecting the Coulomb interaction into flat bands. And what is Coulomb interaction? Well, it comes from density-density type interactions. And so if the charge density is different at these different magic angles, then the Coulomb interaction is going to be different at the different magic angles. So that makes us predict that there'll be a different type of effective Coulomb interaction at the second and third magic angle as compared to the first, and that will probably lead to different types of interacting phases. The other thing that I'd like to say about this is that, as I said, the only difference in wave function between the first, second, and third magic angles is that function rho. And so you can understand where these nodes are coming from, which is these are all solutions. The wave function is always a solution to the Schrodinger equation. And there's going to be a family of solutions, and each one of those is going to be indexed by a different function rho. And so what we're really observing here is that at each solution, that function gets 3 more nodes in the wave function. So here it has 0, then we get 3, then we have 6, because these purple spots are nodes where the wave function exactly vanishes. So that's where these are coming from. They're coming from that function rho, and all the different solutions give us different nodes. And we can actually say a little bit more about these nodes. And so what we see is that I was showing you the wave function just at the K point. So that's a particular wave function, but we can look at other K points that are part of the flat band. And we can also extract those wave functions and plot that wave function in real space. And what we see is that the nodes in the center stay the same. So like if we compare this plot to the plot on the previous slide, these nodes are exactly the same, but there's one extra node that is not the same. And so what happens if you scan across all the different K points is that this node moves all over the place. At each K, it's located at a different R. And that's a generic feature of a churn band. It has a 0, which will scan the entire real space as you vary the wave vector K. but all of the other nodes are completely fixed. And so that means if you were to do an STM measurement where you're averaging the density of states over all the K points, you'd be able to see these nodes because they're there for every single K point sitting in the exact same place. And so this difference in charge density at the second and third magic angle is a feature that we expect could be picked up by an STM measurement. The next feature that we observe, which is different between the first magic angle and the second or third magic angles, is that there's an enhanced orbital magnetization. And so what I'm plotting here is a intra-layer, intra-sublattice current operator. And we're plotting this current operator at the first magic angle and at the second magic angle. We didn't actually look at the third magic angle. I'm plotting it at gamma and then the K points. And so this current operator, its expectation value will have a magnitude and a phase. And so we can plot it on this 2D plot showing those things. And what we see is that if you compare the first magic angle to the second magic angle, in both cases, the current operator has this winding, but the magnitude of the winding gets stronger as you go to the second magic angle. And probably it would also keep getting stronger as we go to the third magic angle. And so we expect that because the wave function is winding around, and it's actually winding around these nodal points, we expect that the orbital magnetization is probably also going to be enhanced as you look at the second magic angle relative to the first magic angle. And this will also probably have an impact on the different types of correlated phases that can be observed. So to summarize what I've shown so far, what we're proposing is that not just the first magic angle, but if we look at the smaller magic angles, there's the opportunity to realize novel physics there. And these are, in summary, the reasons why I think that would be the case. First off, I showed that we get this distinct charge density, which is different at the second and third magic angles compared to the first magic angle. Second, there's also an enhanced orbital magnetization, which is stronger at the second magic angle compared to the first magic angle. And then finally, there's this really interesting comparison to Landau level physics. So let me just say how this works. In the quantum Hall effect, at the second Landau level relative to the first Landau level, you see different types of interacting phases that you don't see at the first Landau level. The most interesting of which is the nu equals 5/2 states, which is believed to host non-abelian quasi-particles. And the difference between the first and second Landau levels and beyond is the node, well, one difference is the nodal structure between these. And because they have a different nodal structure, the Coulomb interaction when you're projected into the Landau level is different, and then you see these different interacting phases. And so if I want to be very optimistic, I can draw a connection between these flat bands and the Landau levels. And then if the first magic angle is analogous to the first Landau level, then the second magic angle would be analogous to the second Landau level. And so therefore, we might hope that we could see different types of exotic correlated phases at the second magic angle, resembling those that are found at the second Landau level. So that's one of the things that makes us believe that looking at these second and third magic angles is a worthwhile pursuit. And I should mention there's some caveat here. So the major caveat is that the second magic angle is more difficult to observe and experiment. And, so what we're assuming here is we're kind of treating the layers as rigid and using this continuum model when we twist the two layers. And in fact, at very small twist angles, this rigid lattice assumption is likely to break down. And so one of the major challenges here is that we'd like to find a platform where the second magic angle is more stable. And I think it's pretty reasonable to think that this might be the case in twisted multi-layer graphene, because there the magic angles are actually larger. The first magic angle is larger, the second magic angle is larger. And so it's reasonable to think that the second and third magic angles might be observable. And then, of course, the other thing that we want to look at is how to extend these results, these observations of charge density and orbital magnetization away from the chiral limit. So far, we've just been looking at this special chiral model, but we'd like to say whether or not we expect these features to be visible in graphene beyond this chiral model. And then, of course, finally, we would like to look at the effective interactions in these at these second and third magic angles and actually confirm or deny whether there's different types of correlated interacting phases that exist there. And we have some idea of how to study this, but this is kind of a challenging problem that we're working on and we'll continue to work on in the future. Okay, so that is what I wanted to say for the first part of the talk. Maybe I should pause for a moment and ask if there's any questions about this.
So maybe a quick question. So has there been any, say, TFT calculation on the second magic angle on how good the approximation of the Chiral limit is?
Yeah, that's a great question. I don't think so. I haven't seen any ab initio calculations for anything except for the first magic angle. And because the angle is smaller, the unit cell is going to be that much bigger. So that's probably, it's going to definitely be a more difficult calculation for something that already was quite difficult.
I see. Do you expect, for example, if you're moving away from the Chiral limit, the number of nodes will be conserved in some sense, or?
This is a great question. So yeah, so we've actually done some work in this direction, looking away from the magic angles. And what happens is that, so the reason that you can get these nodes is basically because you have a two-component spinner. And so it can, it can vanish at points, and then the wave function will wind around those points. Now, if you move away from the chiral limit, then you no longer have this nice feature that the flat bands are localized on either the A or the B sublattice. And so you can't express your flat band as a two-component spinner anymore. It has to be a four-component spinner. And so the nodes, they can lift. They don't need to be exact zeros. They can lift off. And so, so the nodes are not conserved. And so what we see is that the statement that the density of states is different at the second, second magic angle compared to first, it remains, but it's, but you don't get these exact zeros.
I see. Okay, thank you.
Yeah, so probably the projected Coulomb interaction is also still different, but yeah, it's still different, and we don't know exactly what it's going to be.
I see. Okay, thanks.
Great, thanks. So I can, if there's no other questions at the moment, then I will move on to the second part of the talk, which is what the title is based on. So the second idea in this direction that we're working on is we're thinking of different platforms where we can transfer the physics in twisted bilayer graphene. And so one of the ideas that we have is to look at a Moiré superlattice on the surface of a TI. And so I'll say why we want to do this. Let me first acknowledge the collaborators, Xiang, Justin, and Jed that I've gotten to work with. Have been great to work with on this project. So what's the idea? As I said in the beginning, twisted bilayer graphene realizes a plethora of interacting phases due to enhancing the density of states of its Dirac cone. And so you might then want to look for other systems that have Dirac cones and ask, can we also manipulate them with Moiré physics? And so one of the other systems that has a Dirac cone is a topological insulator surface state. So this is, for example, the Dirac cone on the surface of bismuth selenide. And so we want to ask, can we manipulate the surface state by using Moiré physics? And what does Moiré physics mean in this context? Well, what we're really going to do is make a superlattice potential on the surface of the TI and use that to manipulate the Dirac cone. So the similarity to twisted bilayer graphene is that we are making a very large supercell, which has a very small wave vector. And so this kind of periodic potential will fold up the Brillouin zone and create these Moiré Brillouin zone, which has Moiré bands. And the hope is that we can change the density of states here in the same way that I showed you can change the density of states on graphene. But as I'll explain, there's also a lot of differences between these systems. So the first question that you should ask is, why would we want to do this? Why would we want to impose this superlattice on the surface of a TI? And the basic answer is that when we do something similar but different on graphene, we realize all of these interacting phases. And so, and they offer a degree of tunability, which is this twist angle. And so we would hope that if we could do the same thing for the Dirac cone on a topological insulator, that we could realize interaction-driven topological phases, and they would also be tunable. And this time the tunability would come from the period of the superlattice. So that's the thing that we're shooting for. Do we think that this would actually work? Well, at the very least, from a mean field perspective, early on in the field of topological insulators, people ask this question, what about an interacting instability to superconductivity or magnetism on the surface of a TI? And those results using mean field theory showed that if the velocity of the Dirac cone is smaller, which means that the density of states is larger, then you're more likely to realize an interacting phase. And so that's the result that we're going on here. We want to see if we can apply a superlattice, which will change the velocity of the Dirac cone and start to flatten it. And as it flattens it, it will enhance the density of states, and enhancing the density of states will make the interacting phases more feasible. So what we study, so then there's a difference from twisted bilayer graphene, which is that in twisted bilayer graphene, as I showed from the ab initio calculations, you get these really flat bands, and that flat band has a gap to the conduction bands and a gap to the valence band. And that won't ever happen on the surface of a TI, because you can never gap the Dirac cone while preserving symmetry. So that's one of the major differences between the TI surface and the graphene Dirac cones. Now, what we actually do is first we look at the effect on band structure. And so our whole work is saying, how can we tune the surface states of a topological insulator by imposing a Moiré superlattice periodic potential? And so that's the question that we're trying to answer. And the motivation is to study these superconducting and magnetic instabilities, but that part we haven't looked at yet. We're just looking at the band structure physics. And I want to point out that there's two routes to realizing this, which are both actually within the realm of experimental feasibility. So on the left-hand side, what I'm showing, here's the idea. You take a 3D TI, that's what this crystal structure is, and you take kind of a chunk of some kind of dielectric material and punch regular holes in it. That's what creates a superlattice. And then you put your gate underneath that. And so what's shown here is that this there'll be some gate voltage, but it will be screened by the dielectric, and all you'll see is some kind of spatially modulated part, and we're going to treat that as being a cosine potential. So that's how we're imagining creating this superlattice potential. And this sort of setup has already been realized in a few experiments, in particular from Corey Dean's group at Columbia. So this is something which could be done in an experiment on the surface of a TI. The second realization that I'm showing here, this was our initial thought, and you'll see the comparison to twisted bilayer graphene, is that we take our 3D TI, some chunk of material, and we put some 2D layer on top of it. And we want that 2D layer to be lattice matched to the 3D TI. So then if we arrange it with a slight twist angle relative to the 3D TI, it creates some very slowly varying superlattice. And if this thing is insulating, then it's the effect of that superlattice will be some slowly varying potential. And so these are two different physical pictures, which at least in an idealized limit will lead to the same Hamiltonian. It'll be the Hamiltonian of a 3D TI plus some potential, spatially varying potential on the surface of the 3D TI. And we're going to treat that potential to be, to only have one slowly varying wavelength, or in other words, have just one relevant wave vector. And so, so then what we do, which I think is really neat about our work, is that we study this model in three different ways. Perturbation theory, which is analogous to this Bistritzer model of twisted bilayer graphene. And then we use a bulk toy model, the Bernoulli-Zhang model. And then finally, we do an ab initio model. And so all three of these things actually kind of converge and give us a convergent idea of the physics which is happening. And because they kind of agree with each other, then that makes us really trust the results, even though each one of these has different approximations. So starting with perturbation theory, what are we studying here? Our Hamiltonian consists of a Dirac cone. This is on the surface of the TI. And then there's this superlattice potential. And so the effect of a potential is to couple some point K with some other wave vector K plus Q, where Q is the wave vector of the potential. And so we can carry out perturbation theory, and to leading order in perturbation theory, we find that the velocity of this Dirac cone gets renormalized. So it becomes some V star, which is proportional to V, but it has this proportionality constant, which goes like 1/1 plus alpha. So let me just say something about this function alpha here. Alpha has a numerator and a denominator. And the numerator of alpha is the strength of the superlattice potential. So in other words, as we crank up this potential, this term will get bigger, alpha will get bigger, and since it appears in the denominator, the velocity will get smaller. So we can keep cranking up the potential, and this will be one way to decrease the velocity of the Dirac cone, which is what we're after, because the smaller velocity means larger density of states. On the other hand, alpha also has a denominator. So as this denominator gets smaller, that's another way to crank up alpha, which will again make V star, the renormalized velocity, smaller. So what does this wave vector mean? This is the wave vector of the potential. So as the length scale of the potential gets larger, the wave vector gets smaller. And so this can be thought of as saying a larger superlattice unit cell gives us a smaller velocity. And this is analogous to twisted bilayer graphene as well, because you can think of this wave vector as corresponding to the twist angle. In twisted bilayer graphene, the twist angle is proportional to the wave vector, and it goes inversely like the size of the unit cell. So this has a similar feature as twisted bilayer graphene, where if you have a large Moiré unit cell, then you get a more severe enhancement of the velocity. However, the difference, one of the big differences, is that in twisted bilayer graphene, you get these magic angles where the renormalized velocity is 0. And with this structure of V star, we never get magic angles. This function is never equal to 0. It just can keep getting smaller and smaller as we turn up the potential. So that's our first result, which is based on this perturbation theory. And just to put some other picture to this, so suppose this is your Dirac cone shown here. What's the effect of the potential? The potential has these different wave vectors, and it will couple two different K points, which are separated by one of those wave vectors. This is a different way of talking about folding the Bruin zone. And so the result of the potential is that you get this new kind of weird Dirac cone. The center looks the same, but at the corners of this new Moiré Bruin zone, you get what are called satellite cones. So when these 2 points are coupled, they form a new Dirac cone, and that new Dirac cone is living at either pi0 or pi on the surface, Moiré surface Bruin zone. So we get these series of Dirac cones, which we call satellite cones, and we can predict their energy and velocity using perturbation theory. But the other important point is that these satellite cones cannot gap because they're protected by time reversal. So, and so that's why you can't get this gapped flat mini band on the surface of a 3D TI. In twisted bilayer graphene, you get a really flat band, and there's a gap separating it above to the conduction band or below to the valence band. But in this system, you can't get that because of time reversal symmetry. And this is one way of seeing why these satellite cones always have to be gapless. So this preserves the bulk boundary correspondence. And I also want to say, if we look at the density of states of the Dirac cone with a potential, then you can see these satellite cones in the density of states. So this is the original Dirac cone, and you see this nice linear dispersion, but all these other cones correspond to these dips in density of states. Okay, so I showed our perturbative result, which is that we can increase or decrease the velocity of the Dirac cone by applying a superlattice potential in different ways. We can either ramp up the strength of the potential, or we can make a smaller wave vector. But you might be skeptical that this perturbation theory will be effective. There's a couple of concerns one might have, which is, one is that we've assumed the Dirac cone just goes like K dot sigma. So we don't have any anisotropy in our surface states. And the other is that our continuum model is completely ignoring the bulk. It's just looking at the surface. And so to address these concerns, we study two 3D bulk models slab model so that we can see the surface. They have a 3D bulk. So that's what I want to discuss next. So the first model is this toy model. The idea is that we have this 3D TI, we have a 2D insulator on top of it, and we range them with this slight twist angle. So there's some coupling between these two different layers. That's what this part of the Hamiltonian is meant to capture. And if we assume that this 2D layer is an insulator, then we can just integrate it out. And so when we integrate out the insulator, then what we're left with is some kind of effective potential on the surface of the Dirac cone. And that effective potential ends up being quadratic in the interlayer coupling. So there's some coupling between the TI and the 2D layer. If we integrate out the 2D layer, we're left with an effective potential on the TI, which is quadratic in the original coupling. That just comes from the integrating out. So the potential takes on kind of a weird form, but we know exactly what that form is. And so the reason that I'm saying all this is just to say, we now put this potential numerically on the TI surface. So we study the Hamiltonian of a TI with the potential on the surface. And the potential that we study is not just two different cosines, but it has these additional cosines because these are the leading order terms when we integrate out that 2D layer. So just to kind of summarize it, we're putting a potential on the 3D TI surface, and it has kind of a weird form. And the reason that we chose that form is because that is what it's the form that follows from this kind of twisted heterostructure. So now I can show these numerical results and compare them to our perturbation theory by plotting the velocity of the Dirac cone as a function of the strength and wave vector of the superlattice potential. So first, this first plot is plotting the velocity of the Dirac cone for fixed wave vector, but changing this, it's really the interlayer coupling strength in our model, which is playing the same role as the superlattice potential. And so this is the original Dirac cone velocity in units of itself. So it starts out at 1. And as we increase the potential strength, we see that this velocity starts to nosedive. And so the dots are the numerical results for different values of potential strength. And then this line is our perturbation theory, which we've extended to 5th order so that it goes out a lot further. And so you can see that the perturbation theory and the exact diagonalization of this model agree pretty well. And then eventually they start to deviate, but they both show that there can be a dramatic renormalization of the Dirac cone. And in particular, our numerics show that the Dirac cone velocity can reach about 0.4 of its original value. So that's a pretty significant renormalization. And then it starts to go up. And what we were plotting here is the velocity of the satellite cones that I mentioned. But the important feature is that the Dirac cone velocity can be significantly changed by over a factor of 2. Now we can also make a kind of plot the inverse, which is we plot the velocity of the Dirac cone, we fix the magnitude of the potential, but we vary that the wave vector q. And so now same thing, the dots are our numerics and the lines are perturbation theory. And we can see that as the wave vector of q, the wave vector q gets smaller, then the velocity also starts to nosedive. And so that agrees with our perturbation theory. And you can see that the dots are actually agree very well with the perturbation theory, which is shown by this line. But the thing that's interesting is that here also the Dirac cone velocity drops down to about 0.5 of its original value. Maybe it would keep going. This is the largest system size that we could consider. Over here, actually, it looks to be about 0.4. And so we see that no matter whether we're varying the superlattice potential or its wave vector, we seem to max out at about the same value, which is the velocity is around 0.5 or 0.4 of its original velocity. And we can also plot the band structure with this superlattice potential. And so this is having a very small potential. And so we see that it's basically just the Dirac cone with small modulations on top. But as we ramp up potential, we start to see the emergence of these satellite peaks that I was mentioning. Those are all these dips in the density of states. And as we continue to ramp up, one of the interesting things that happens is that these different satellite cones move around in energy. And when they align with each other, you actually get a really flat band. So this is something that we see here. It's a really flat band with a big peak in the density of states. that you can see. And this is different than what we were originally looking for. So originally, what we're looking for is we want to change the velocity of the Dirac cone, and we want to see an enhanced density of states from decreasing that velocity and making as flat of a Dirac cone as we can. But what we see is that actually one way to get a very large peak in density of states, larger than all the other peaks that we see, is something that we didn't originally think of, which is when the satellite cones align with each other, that also is a different route to getting you a pretty flat band. So then we want to ask, for this final investigation, how does this toy model actually work for real materials? And so what we originally considered doing was, let's look at hexagonal boron nitride on the surface of bismuth selenide. These things are lattice matched up to a factor of √3, or nearly lattice matched up to a factor of √3. And so it seemed like a reasonably good candidate. But the problem is that actually the Dirac cone in bismuth selenide is quite steep. And so this wave vector Q that comes out is too big. What we need is some wave vector Q that just mixes the surface states with each other. But when Q is too big, it'll start mixing the surface states and the bulk states. And then our theory is going to break down. And so we realized that it's going to be quite difficult to make one of these twisted heterostructures on the surface of, say, bismuth selenide, which is in this family of the most famous 3D TIs. And so this leads us to the other idea that I mentioned, which is that instead of making a twisted heterostructure, why don't we make this patterned potential on the surface of a 3D TI? And so then you can actually control the strength and the period of the potential. And that plays the role of a twisted heterostructure, but is a lot more controllable. And as I mentioned in the beginning, these sorts of experiments have already been done by Corey Dean's group on graphene, not on the 3D TI. They've done it on graphene. And so they were able to make these potentials where the period of the potential is around, say, 35 nanometers, and the potential strength is going up to about 50 MeV. So what we do is we're going to model that potential on bismuth selenide through an ab initio model. Previously, I don't think I said this, but in our previous toy model, we were just using the Bernavig-Hughes-Zhang model in 3D. So it's a toy model of a 3D TI. So here, what we do is we make a slab of bismuth selenide. So it's 5 quintuple layers. That's what this gray band structure is showing. And on top of the gray is the band structure of our Vannierized type binding model. And so you can see, so I'm then zooming in on this Dirac code, and what you see is that the red bands are our type binding model, and the gray bands are the full ab initio calculation. And near the Dirac cone, these things agree quite well. Beyond, for the higher energy physics, they differ, but for the low energy physics, they agree. And so we're pretty happy with this Vannierization. So then what we do is we make a slab model using this Vannierized type binding model and impose this triangular periodic potential. And we take the length scale to be 12 nanometers in real space, which is about the same as the Moiré unit cell and twisted bilayer graphene, and a bit smaller than can actually probably be realized in these dielectric experiments so far. And so now we can compare the sorts of plots that I was showing you before. On this left-hand plot, we're just plotting the energy of the Dirac cones. And the reason that we did this is to compare our perturbation theory to the numerics. But to compare to the other plots we've been looking at, we should look at the velocity of the Dirac cones versus the potential strength. So we fix the superlattice length scale, but we can vary the potential strength. And this red band is our original Dirac cone. And so its velocity is 1 in some units if we don't imply any potential. And then when we start ramping up the potential, we see that the velocity significantly decreases, and it goes down to more or less about 1/3 of its original value. And so this is actually, it's a completely different model, but it's actually agreeing with our toy model where the velocity dipped down to about 0.4 or 0.5 of its original value and then starts coming up again. And so I think this is what gives us a lot of faith that this model might be a pretty good description of the physics, is that these things actually agree with each other, even more or less quantitatively. These purple and blue and green lines are plotting the velocities of the satellite cones. And so So I wanted to point out that actually one of the other things that emerges here is that you get different satellite cones at gamma at different energies. And one of these satellite cones is actually flat. What that means is that it doesn't have a linear term in its dispersion. It has a quadratic term, but we're only plotting velocity, which is the linear term. And so this is yet another route to realizing flat bands on a TI surface, which we didn't set out to look for, which is that the satellite bands can have zero velocity. And that's exactly what we see here. And so we can also make these same kind of density of states plots as a function of turning the potential up, and we can track these different Dirac cones, and we can also that gives us some way to understand these different peaks in density of states that emerge as we turn up the potential strength. So I want to so I'll summarize here. What we're looking at here, or our main result, is that we can dramatically renormalize the surface states on the surface of a topological insulator by applying a superlattice potential. And we've shown this in a few different ways, perturbation theory and exact numerics. And we've looked at these two different models with the numerics, this Bernoulli-Hughes-Zhang kind of toy model, as well as our ab initio model of bismuth selenide. And we see that there's three different ways to enhance the surface density of states. First off, we can renormalize the velocity of the original Dirac cone down by a factor of 2 of its original velocity. And that's one of the things that we're seeing here. And that was what we originally set out to do. Second, there's for specific fine-tuned values of the potential, there's regions where different satellite cones align with each other. And that's a way to get really flat bands on the surface of a TI. And then third, it's possible that the satellite cones can have zero velocity, which is what's being shown down here. And that's a third way to get flat bands on the surface of a TI. So we can see that there's three different routes to get flat bands or flatter bands on the surface of a topological insulator. And these flat bands will renormalize the velocity, in one case, renormalize the velocity of the Dirac cone. But importantly, they give us an enhanced density of states. And it's this enhanced density of states that is a good thing for realizing interacting topological phases. So that's what makes us excited about this result, our ability to tune the surface Dirac cone and in such a way that would be favorable to realize interacting instabilities. And so the places that we want to go with this are first off to find better material candidates in order to make these types of twisted heterostructure superlattices. Second, which we're already working on, is to ask, well, instead of putting an insulator on the 3D TI surface, what if we put some gapless material like graphene? How does that impact the surface states? And then finally, there's this question about asking about these interacting instabilities. And here I just want to mention a really interesting paper by Liang Fu's group that came out at the same time as ours, where they're also looking at a superlattice potential, but looking at different aspects of it. And they compute the superconducting TC for this fine-tuned value of potential, which leads to higher order Van Hove singularities. And there, what they see, which agrees with our results, is that if you enhance the density of states on the surface of a TI, you enhance the interacting effects, great, but they go further and in this particular limit, compute the superconducting TC and show that it scales polynomially with the electron-photon coupling, which is an improvement over the usual exponential scaling. And so I think that looking deeper at the interacting instabilities or looking at their model in a more combined with the ab initio models that we have here could give really interesting, more accurate predictions for the interacting instabilities on the surface of a 3D TI. So I'll stop here, and if there's any questions, then I'd be happy to spend the last few minutes taking questions.
Oh, is this the last slide?
Yes.
Okay, great. Thank you very much. So yeah, so now it's a Q&A session. So if anyone has any questions, just unmute yourself and just speak up.
Okay, very nice talk. First, I have some questions for this. So you are talking about putting this topological insulator onto a superlattice. So how does this period of superlattice affect this effect? You mentioned 35 nanometers, for example. In reality, actually, it's roughly that range. So will this affect your results?
Yeah, so, well, let me just answer that question, and then you
Yeah.
can also ask another question. Right, so what we did was I wrote this in terms of wave vector, but we fixed the wave vector, and I think this corresponds to a smaller length scale than 35 nanometers, closer to 12 or 15 nanometers. We fixed that, and then we looked at how this velocity changes with potential strength. But we could have done something different like we did in our toy model, which is we could have fixed the potential strength and varied the length scale. And what I expect would happen is that longer length scales are more favorable for us. We see this in our perturbation theory because the longer length scale corresponds to a smaller wave vector. And that's what increases this new renormalized velocity. So I think that if we moved up to 35 nanometers or even longer, then I think that in our model, we would see an even flatter Dirac cone, but there's also an upper bound on the size of these superlattices. We're considering a perfect model. We're not considering any disorder, or any other effects that are going to cause decoherence.
Okay, great, thanks. So another question is, how about you are mentioning that you are looking for different material that goes, right? So there is one material which is a 2D, like layered this topological insulator, like magnesium bismuth telluride, right? So that one is very popular, and also recently we also observed this quantum anomaly Hall effect in it.
Right.
So how about if you put that one onto this kind of superlattice, and what do you get?
So I think there's a few different directions to take. One direction is if you look in the magnetic phase of manganese bismuth telluride, it might realize a magnetic TI, right? And so then it would have multiple Dirac cones on the surface. And so that would be really interesting. And so I think that what I would expect is that the superlattice potential that we're putting on our single Dirac cone on a regular 3D TI, you basically get kind of double the effects. The same effects would happen for each of the two Dirac cones that could appear on the magnetic TI. Now, there's a different aspect to this, which is that the magnetic TI obviously breaks time reversal. And so then you could actually realize a gapped miniband. So that's, here we're always keeping time reversal because we're not studying any interactions. But if you, so I think in the magnetic TI, you could see something different, which is that you could open a gap to that flat band. And I think that would be pretty desirable because then you could create a gapped flat band, which is even more analogous to twisted bilayer graphene.
Okay, great, thanks.
Okay, thank you, Weibo. Any other questions? Maybe let me ask one question relating to this slide. So in terms of future directions, the second one, extension to gapless 2D layers. So I think in your calculation, when you're putting a superlattice on the top of the TI, you're adding, from a theoretical point of view, just a one-body potential to the original Hamiltonian. Right. So how is this gaplessness of this 2D layer going to affect the?
Right, exactly. So we would do something. So this is, we have some results in this direction already. It's a different calculation where instead of having a potential, we would actually keep the interlayer coupling. So you tunnel TI to say graphene and then back. And so, so that's why we expect that you would get something, you get something different because it's actually a different model.
It's a more coupled model.
And so it's more similar to the Bistritzer-McDonald model. It has more Dirac cones involved. So that's why we wanted to do it.
I see. Great. So another related one is.
Can I have one question?
Oh, sure. Please go ahead. Yes.
Then I start. I was wondering, is there any trade-off that we should consider so as to combine one, let's say, two of these ways to enhance the surface density of states? Could we have all three effects in the same system, or two of them?
Yeah, let me say something about this. And so, so this first point is changing the velocity of the Dirac cone, and that's a pretty general effect, which will get more enhanced as you change either the wave vector or strength of the potential. These last two require, at least the second one requires some fine tuning. The satellite peaks only align at particular values of the your superlattice potential. So those things can be combined with each other, but this is kind of more fine-tuned. And then this last point, we should actually study the density of states more. So what happens is that you get a particular satellite cone with 0 velocity, but it has a quadratic dispersion. So usually quadratic dispersions are flatter than linear dispersion, because the density of states will increase slower. And actually, this one is also pretty generic for 6-fold symmetry. It doesn't happen it's a feature of 6-fold instead of the 4-fold symmetry that we used in our toy model. So yes, actually, these things can be combined. And I'll say something else, which is what Liang Fu's group studies, what they call higher order Van Hoff singularities. That's also fine-tuned. You basically have different Fermi surfaces, and exactly when they get pulled to a point where they're touching at their corners tangentially to each other, that's also when you get an enhancement in density of states. So combinations of these can be realized, and maybe if you realize that in a suitable way, you can actually even further optimize your effects. That's a really good point.
Great. Okay, more questions. We still have time.
Hi, Jennifer. Thanks for your talk. So my question is, so is the second magic angle, like, is it related to the normal magic angle? Is the number related somehow, these angles?
Right. So yeah, let me, I can go back here. I think the answer is that's not related in an obvious way. So,
Okay.
so let's see, somewhere in here. Right, these are the different magic angles. So you can see this is in the Bistritzer-McDonald model. These angles are, in some limit, they actually become evenly spaced, or I think inverse evenly spaced. But in the more realistic situation, there's not an obvious pattern that links them. They're just solutions to some complicated equation. Right. The only thing is that, like I said, 1.1 degrees is the biggest, and all the others are smaller than that. But yeah, they're not obviously related to each other.
Okay. So is it the trend only for graphene, or this is applicable for other materials as well? This trend we're seeing?
So, oh, right. I think it depends. So what are the other materials we might want to consider? So far we looked at graphene.
Yeah.
Oh yeah, so you could look at twisted multi-layer graphene, and there I expect that you would see something similar because it's pretty similar to twisted bilayer graphene. But you could also look at like twisted transition metal dichalcogenides, and there the physics is a little bit different because you don't realize magic angles. You realize kind of a continuum of effects, but there's no place. So I don't know if you've studied this or not, but in the twisted TMDs, you basically get kind of like a W shape. You don't have a flat band, but it has a region which gets pretty flat, and you have a Van Hoff singularity, but you don't have a magic angle. And so there, I don't expect that I expect that it might be a different story.
Okay. Yeah. Thank you.
Yeah, thanks.
Okay, thanks. Other questions?
Hello, Jennifer. I have a question on that.
Good.
Did you consider about the relaxation effect when you calculate the band structure?
Your question was about relativistic effect. Is that what you said?
Sorry, relaxation.
Oh, relaxation effects.
Yeah.
Got it. Yeah. So our model, we're not doing an ab initio calculation. We're doing a continuum model, which means that we're taking linear Dirac cone in one layer, linear Dirac cone in another layer, and coupling them. So there we've lost our notion of a lattice anyway, so there's nothing to relax. So I think, I think there the answer is no. And this is an idealized model anyway. So this chiral model that I was mentioning, what this model is your two layers, they can have AA and AB coupling, and it only keeps the AB coupling. So it's a very idealized model, which has nice analytical properties and nice spectral properties. but it's idealized. And so, like, for example, this is the ab initio band structure where the bands are relaxed. We don't have even a mechanism for doing that in our model.
Okay, thank you.
Thank you, Sung-Ho. More questions? Okay, maybe I'll just ask a more speculative question about the last part of the superlattice. So when you add a superlattice, you're renormalizing the velocity, the Fermi velocity, and increasing the density of state. And of course, the interaction effect is getting stronger. So without doing a detailed calculation of the interaction, do we have any idea if this interaction is going to open up a gap at the surface? Is it possible?
Yeah, so right. It depends on exactly what you're looking at, but if you look at the most common interaction, so like suppose that we did mean field theory, we would either look at probably superconductivity or anomalous quantum Hall, some type of magnetic order. And both of those can open a gap because they break symmetry. So if you break time reversal symmetry, then these gapless satellite cones can become gapped. And if you add superconductivity, then you can also, you'll open a gap at half filling. So yeah, I would expect that both of those things can open a gap. And a person might ask, does the nature of that gap also change the density of states in some favorable way? Probably yes, because anytime you open a gap, you're kind of further flattening out the bands.
So in principle, opening a gap is by some spontaneous symmetry breaking,
Yes.
time reversal symmetry. But for the topological insulator, you have one cone on the other one side, one surface. It's a time reversal partner is sort of like the opposite side, right? So so that's why I'm asking. So interaction-wise, is it still possible to have this kind of spontaneous symmetry breaking, or?
I don't really see why not. You know, the two surfaces are far apart from each other. So what I would expect is that the one surface would become gapped and the other surface would remain gapless. Since you've broken time reversal on one surface, you know, there's going to be some exponential effect on the other surface, but that will be quite small. So I think you'll gap one and the other will be gapless.
I see. Okay. Okay, thanks. Any more questions before maybe we can entertain one more question? Justin just joined us. Okay, so if there are no more questions, let's thank our speaker again. Thank you very much, Jennifer, for the very interesting talk.
Yeah, thanks for all the questions and thanks a lot for the invitation.
I think just